So we are very happy to have Professor Raghuvan Saxena here with us today, and it's extremely fortunate for me, especially that he agreed to give a talk on this recent paper on equiangular lines. It uses spectrography in a very cool way. I want to understand how it exactly uses it, and I'm looking forward to his talk. Among other things, Raghuvan is an absolute pleasure to talk to. I mean, conversations are very mind opening, and if you are planning on watching Dhurandhar 2, this is a Dhurandhar person at work, so
Okay, so I want to start with a story that you all know. The story goes that Ramanujan was sick in a hospital, and his friend Hardy came, and he remarked that I was driving, the cab that took me here had the number 172. Okay, thank you. Okay, so Hardy came and he remarked that the taxi I drove on had a very unremarkable number, which was 1729. And Ramanujan immediately said, no, it's actually quite remarkable because it's the only number that you can write as the smallest number that you can write as a sum of two tubes in two different ways. Yes, this is a very well-known story. On my way here today, I saw a Mercedes, which has a logo roughly like this. And as you can see, there has an origin here. And then there are three lines from the origin such that the angle is the same. So I'm going to talk about equiangular lines. That is the topic. And the question is very simple. You're given a dimension D. You're given an angle theta, and you want to find what is the largest number of lines through the origin. Let's say in RD, that's where in RD passing through the origin. Such that each pair has an angle theta. Such that the angle between each pair of lines equals. Okay, so this is the question that we will study. I will show precise bound. So we'll nail the main term, we'll nail the most significant term. After that, we'll have some lower order terms that we won't care about. But before we go there, first I'll do is I'll rephrase this same question in a couple of different ways to eventually get to a problem that I can say it's a spectral graph theory problem. So it's worth to talk about this here. So the first thing I want to do is because all of these lines are passing through the origin, what I have is I can identify a line I by the unit vector Vi. So you have a line that goes through the origin. The unit vector is just a vector of length 1 that is on that line. And because it goes through the origin, it is one-to-one correspondence. Every line has a vector, every vector is a line. Okay. Once I write it as a unit vector, to define the angle, then I just have the angle between I and J is just the inner product of Vi and Vj, because the magnitude is 1, so it is not necessary to write it. The angle is just the inner product. So I can say what is the number of unit vectors such that the pairwise inner product is this. This is not quite the case because there is a distinction between lines versus vectors. So what happens is if I have the origin somewhere here and I have these two vectors, let's say this is the vector. So this is V1 and this is V2. Then treating them as vectors, it gives me an angle which is just the angle of V1 minus V2. But to treat them as lines, I actually get two vectors, two angles. So I have this angle and I also have this other angle. So it's either V1 minus V2 or V1 plus V2. This talk is about equiangular lines. So we'll be talking about this version where the angle is always smaller than 90 degrees. Because if it's more than 90, I can just state the other side, it will be smaller than 90 degrees. But for the next maybe 5 minutes, let's just settle the case of vectors also. You can imagine the same question. So you could imagine I'm taking the one that's less than 90 degrees. For the vectors, it's well defined. There's only one angle. It could be larger than 90. It could be opposite, like these should be vectors. Yes, very good. Yeah, I was about to say that. So yeah. I was about to say that also. So let us see. I'll say that now. So this is a question about equiangular lines. You can ask the same question about equiangular vectors. Everything is the same, except now I have a set of vectors to the origin such that the pairwise angle between every two vectors is theta. Okay. So this question is actually
set of points in three dimension and you want to place them so that the minimum distance between pairwise distance is at least some delta.
Yeah.
So is it related to
so that is more like a packing problem. So I've seen this in many contexts where suppose you are putting things in the Boolean cube and then you want to place points. So this is, for example, a code thing. Like if you have code words and you want them to be, there needs to be a Hamming ball around them that needs to be disjoint. So that is a packing problem.
because I feel like, so for example here, right, like if you maintain certain minimum angle that allows you to have points to be at least maintaining certain distance, right? So it's like if you want to maintain like certain distance between pairwise points, you are expecting that.
There is a difference. The key difference is in all those packing problems, typically you have something like greater than. So you want the distance between any two code words to be at least something. Here it is an equality. And the answer changes drastically. So code words you can have exponentially many in n dimensions, you can have roughly 2 to the order n. Here it will actually be linear, something like that. So the answer changes. One example to keep in mind is, is the Hadamard code. In the Hadamard code, the distances are exactly half, and there the number of code words is equal to the dimension of the space. So there is not exponential. Okay, so yeah, the vectors thing. So you could ask the same question about vectors, and there it would be you have a set of vectors through the origin, and you want to have the condition that any pair of them has the same angle theta. How many such vectors can be there? There is a way to prove that. It's like an exercise. It also follows from what we'll do today, but for now I'll just give you the answer. Once we have the whole lecture, you can go back and see that the same techniques will give you this answer. So in the case of vectors, if so let me give this a name. Let me call this actually just V theta d. So this is the maximum number of vectors, pairwise angle is theta, dimension is d. So if V theta D is equal to it is equal to D. Let me say the other thing. It's equal to D plus 1 if theta is equal to cos inverse minus 1 over D plus 1. We'll make sense of this number. And for everything else, it is D. So what is this number for D equals to 2? This is cos inverse, is it D plus 1 or D? It is cos inverse minus 1/3. Is this correct? It should be half, I think. Huh?
Looks like it should be cosine inverse negative over D plus 1. What do you have?
Yeah, I think it should be 1 over D. Let me just, anyway, whatever works. This is the, yeah, the answer is I think this. Else it is, any other theta not equal to this. Okay, so for every other than one angle it is this, for exactly one angle it is D plus 1. And so let's put D equals to 2. Cos inverse of minus half, it would be 120 degrees. So when the angle is exactly 120, you have 3 different vectors. At any angle, you will find it hard to fit 3 because once you fix this and this, then this would be automatically be fixed. Okay, and the same idea extends. So if you have, if you're working in a dimension 3 space, you can sort of pull these things forward to change the angle, but there will be a unique point where you can also have the extra ray going backwards. So that gives you an extra plus 1. Other than that, you just have D. So this is the answer. I will not prove this, but whatever we'll do in the lecture will sort of cover this. It is enough. There are easier proofs also, but it will be enough to, yeah. Yeah, that is one other way to prove it. We'll see parts of the technique also. Yeah. But this is a much simpler problem. The question we'll be working with is lines. And there the angle is not just this, it could be 180 minus this, it will be the smaller one. So in the lines interpretation, let me get rid of this. Okay, so in the lines interpretation, the angle is always less than 90 degrees because if it's more, you can just state the other side. And that means that the angle is actually the absolute value of the inner product. So that's all that changes. You put 2 extra lines because they are lines, and that is the condition we want. So the question is that we want given a dimension D, given a dimension D, so the angles are between 0 and 90, theta and cos theta are in a bijection. I'll just say what is cos theta. And value alpha, this is in 0, 1. What is the largest number? So now I can use the same notation. Let's call it n alpha d, number of lines in RD. So these lines such that for all I not equal to j, I'm writing the same thing. Alpha. Okay. So I'm writing the same question in terms of lines. That's why we have the absolute value, and VI's are the unit vectors in that direction as before. Okay. Now, as Akash said, this interpretation is what leads to Gram matrix. Okay. The Gram matrix is defined by a set of vectors. So here our vectors are V1 to, let's say, Vn. Okay. And the ijth entry in this matrix is just Vi inner product with Vj. So this is V1, 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 V2. So on. Okay. So this is a Gram matrix is defined by a set of vectors. You can also view it as a matrix V in, I think it should be D times N. So the vectors are columns, and then the Gram matrix is just V transpose V. So, okay. So our question now is, given a dimension V, what is the largest matrix in terms of the number of columns? V, such that V transpose V has the form. They are unit vectors. So what would be the diagonal elements here? 1. And we know the inner product between any two different I and j is alpha. So all the off diagonal entries would be on the vector. Okay. So our question is, given a dimension D, what is the largest number of vectors n such that once you compute the Gram matrix, then it has this form. It has 1 on the diagonal, and the magnitude of every other entry, it's plus minus alpha. So you also given alpha. Okay. So the next thing I want to do is I want to get rid of these vectors completely. I just want to work with this matrix because this matrix will eventually become the adjacency matrix of a graph. Okay. So I want to get rid of this, and the way I can get rid of this is by observing that this thing is always symmetric. Okay, you can take its transpose, it will be the same. And the other thing is, I mean, there are 3 things. So the second thing is it is always positive semi-definite. Is there somebody who's not familiar with PST? Speak now or forever hold your peace. So yes, a little bit, but let's just write it. So a matrix M is PST is if and only if for all vectors x x transpose M. Yes, so in this case you will have, so this is the norm of Vx basically squared, which is non-negative. So it's Vx in a product with itself. Okay. So this is the first property, this is the second property. The third property of this is that its rank is less than or equal to D. Why is this? Simply because it's coming from points that have D dimensions. So this vector, the V D times n, it cannot have rank more than D because there are D rows. And the null space of D is also the null space of that. So the rank is at most D. Okay. So we want matrices that are symmetric PST with rank less than D and look like this. Okay. Now, the cool thing is, this is like a fact. Let me make sure nobody fact checks me. For any real, it will be real throughout. So let me just say for any symmetric, yes. For any symmetric matrix M, we have M is PST with rank less than equal to D, if and only if we okay. So saying that it is PSD and rank D, it is the same as saying that is in this form. That's what this term is saying. If your matrix M is symmetric, then saying that it has PSD and rank D, that happens if and only if you have a decomposition as V transpose V. This fact, I teach it in my intro linear algebra course. Also, it's a standard fact. Basically, some people say it as if PSD matrix has a square root. So you can write this as the square root of the matrix. V is not unique. You can, for example, negate it. Minus V would be something. We also do some other operations. V is not unique, but the rank, there's a minimum rank of V that is unique. You can write some dummy zeros, but other than those things, the rank is the same. Okay, so I don't have to say all of this vectors business. I just have to say symmetric and rank D. Okay. So what is our question now? The new question. Let me just write it. Given a dimension D and alpha, given D and alpha in 0, 1. What is the largest n for which there exists a symmetric M of this form. So I don't know how to call it, but whenever I say of this form, I mean it has ones on the diagonal and alphas outside. So of this form, that is PSD with rank less than equal to D. Okay, it's the same question. That's what I want to say. This question is the same as this, which is the same as this, because if I have such a matrix, it promises me a vector matrix V, which is a set of vectors. V transpose V will have the property that it has ones on a diagonal and plus minus alpha outside, which means that the pairwise inner products are all alpha in magnitude, which is what we wanted. Okay. So this is the same question. Here we don't have any vectors, nothing. Here is a clean question about matrices. Now we'll go to graphs, and then that will be the question I eventually study. Okay, so now we have removed the vectors. We are on matrices. Now we'll get to graphs. Okay, so let us see what exactly this form is. It has ones on the diagonal, so it has some identity component. The other things are, imagine they're all alpha, then it's, so suppose everything was positive, then it would just be J, where I is the identity and J is equal to 1 transpose, it's the all ones matrix. Okay, so if you did not have the signs here, if everything was alpha, then I'm just saying a matrix of this form. This is quite close, except that you have some signs. So let me define a graph let's say on N, such that I is connected to J if and only if this is, so M Ij is less than 0. Okay, So this graph has an edge if and only if the sign here is negative, which means the adjacency matrix of this graph, it says everything I need to know about this matrix. Specifically, what I will have is M equals all of this I will move this here. Let me write here plus alpha j. And here I have minus 2 alpha times g. So g I will use to denote the graph. G will also denote the adjacency matrix of the graph. They will both be g. Here it's the equation of matrices. So here it's a matrix. And I claim that if you have the signs determined by the graph, then the matrix is just this. Why? Well, we know this term and this term give me 1 with plus alphas everywhere. And what this does, it subtracts 2 alpha from whenever you should have a negative sign. So all the plus alphas there, they become minus alphas, so you get exactly that matrix. Okay. One more thing, because we're talking about symmetric matrices, this graph is actually quite nice. It's an undirected graph, everything is a simple graph, everything holds. So this thing is 1 minus alpha by 2 alpha times 2 alpha times 1 minus alpha by 2 alpha I minus g plus j over 2. I am writing it this way because these two properties, that it is PSD and rank, it is not affected by scaling. So all I want is this parameter lambda, and then I just want lambda minus g plus j over 2. Is this readable from there? Okay. So I just want this part to be PSD and has rank. I'll write it there also. Okay, so our question now is given lambda, which in terms of alpha is just this, and d, what is the largest graph? Largest in terms of the number of vertices. This graph should have a lot of vertices. Largest graph G such that lambda I minus G plus J over 2 is PSD rank less than equal to. Okay. So all we have done so far, we've not actually done anything about the question. We have just restated it to get to this graph theoretic language. The first thing we did was we had this talk about lines versus vectors. We're talking about lines, so everything has a plus minus. Then we got to this matrix. The matrix was easy to describe. There is this alpha component that is captured by J. There is the diagonal that is captured by I. And then there are the signs that are captured by the graph. These are the most important things. So we isolate that structure as a graph. And the rest is just the alpha component. We will prove, yeah, both directions. Not equality, but D plus O of D, right? Something like that, yeah. Yeah, so we want the largest graph such that this matrix is PSD with rank less than equal to. This is our question. Let me erase the rest of it so you can focus on this. Okay, so we started from lines and angles. We have reached graphs. The next thing I want to reach is spectrum. So I want to talk about eigenvalues of this graph, specifically of this matrix. It's a symmetric matrix because it's an underrated graph, so it has a full set of eigenvalues if we count them with multiplicity. So you want to talk about those eigenvalues. And specifically, what I would want to show is, what I want to examine is the multiplicity of this lambda. How many times is lambda an eigenvalue of G? Okay. The proof we'll divide it, yeah. So this thing is singular if and only if lambda is an eigenvalue, that's why.
We want it to be singular, yes.
Yeah. So anyway, so this J thing, by the way, is a rank 1 matrix. So this thing does not really matter. I can make D and D plus 1. The real thing is this, which is where the eigenvalue thing comes in. Okay, so what I want to do next is I want to relate this question to the multiplicity of lambda in this matrix, in the eigenvalues of this matrix G. So let us do that. We'll do some cases. So the first case would be the easiest one. What happens if the multiplicity is 0? What happens if lambda is not an eigenvalue? Okay, so if lambda is not an eigenvalue of G, then I know that the rank of lambda I minus G is equal to m. Okay, this is a full rank matrix. If it was not a full rank matrix, there'd be something that will vanish, which would mean we would have an eigenvector, which would mean lambda is an eigenvalue. So the fact that lambda is not an eigenvalue tells me that this is full rank. Okay. This is a full rank matrix, this is a rank 1 matrix, so I can conclude that the rank of lambda I minus G plus J over 2 is greater than or equal to n minus 1. Okay. I want it to be at most D. So what I get is n is less than or equal to D plus 1. Okay, so if lambda is not in the spectrum of G, then the graphs cannot be large. I have this D plus 1 bound. This is what we are getting for vectors. This is a simple construction. It's a very small bound. So for example, to get D, you don't even need the minus alpha. D you can get without the minus alpha. This is very close to it. So this is a very strong bound. If it's not in the spectrum, then you have n is at most D plus 1. Okay, that is the first case. The second case, 2, is now lambda is an eigenvalue, and now I'll assume that it's the largest eigenvalue. Of G. So in this lecture, I guess, I'm going to use the largest eigenvalue and also the phrase spectral radius. These are the same for graphs because the matrix is positive, all the entries are positive, so I will use them interchangeably. Yeah, but this is a positive matrix. It is not positive semi-definite, it's entry-wise positive, which means by Perron Frobenius, it's not really the Perron Frobenius because it could be 0, but roughly by Perron Frobenius, the largest eigenvalue will be the positive one. No, not for positive matrix. That's what Perron Frobenius says. No, it could be minus alpha, yeah, but it can't be more negative than minus alpha. So it will still be the spectral radius. The spectral radius would just be the largest. Yeah, it cannot be that you have alpha here minus 2 alpha there. Then the radius would be 2 alpha. But here it's the same because it's a positive thing. Like I'm going to use these things interchangeably. That's all I'm saying. Another thing I'll use, I'll just call it lambda 1 of G sometimes. because this is the largest one. The second largest one will be lambda 2 of G. So they will all be the same thing. Okay, but anyway, so we did the easy case where it's not in the spectrum. Now I'm saying it is in the spectrum, and I'm also saying that it's the largest thing in the spectrum. What happens in this case? Okay, so in this case, I want to consider yeah.
We only have an upper bound on the number of equivalent lines with angular alpha. Do we have a lower bound?
I will come to lower bounds. So D is something you can get without even the minus sign. You definitely have D. This extra plus one I don't really know, but I'll come to lower bounds later on if we have time. Lower bounds are actually, so the reason I'm doing upper bounds first, they are the interesting ones. If I tell you the lower bounds, it will seem obvious after the, we'll just be seeing every inequality and you want it to be tight. So that's the lower bound construction. Okay, so we are in this case where lambda is the largest eigenvalue of G, and what I want to do is I basically want to say that lambda does not have a high multiplicity. Okay, now when can I say this? So suppose this matrix G, let me recall this for Perron Frobenius. So it says that if a matrix is entry wise positive, it says a lot of things, but for example, one thing that the largest in magnitude is positive. It also says that it is unique. So you don't have a multiplicity on the highest one. You can have a multiplicity below it, but not on the highest one. And it also says that has an entry-wise positive eigenvector. No, I mean positive. Also here I mean positive. This is actually something, it's a good thing you asked because this is what I was going to stress on. So Perron Frobenius only applies to positive matrices. It does not apply to non-negative matrices. There is an easy counterexample, just consider the zero matrix. Okay, all eigenvalues are zero, there is multiplicity, they are not unique, blah blah blah. Nothing holds. Yes, this one. This one does not lie. This one. It is unique, it is positive. Yeah. Yeah. So we'll use this repeatedly, but what I want to say is imagine this G, it's not positive because, for example, the diagonals are zero, there are no loops in the graph. It's not positive. But if this were positive, then this would, Perron Frobenius would directly tell me that the multiplicity of the largest one is 1. Then I won't have to do anything. So G is the adjacency matrix of a graph. It has zeros on the diagonal because it has no self loops, which means it's not positive because it has zeros on the diagonal. So you cannot apply this. Okay. But how do we make it positive? You simply consider paths instead of edges. So you consider the matrix. I want to preserve the sign, so I'll make sure it's odd, but I don't think it's necessary. Consider the matrix G to the 2n plus 1. Okay. So if a vertex can reach any other vertex, then that entry will be positive here. So this will just be, this matrix would look like, you have the connected components of G, so you have C1, C2, let's say you have 3 of them. then all of these entries will be positive, and all of these things would be 0. Okay. This is what this would look like. So just by taking the powers, I can break it into blots that are positive throughout, which means I can apply Perron-Frobenius. Actually, I'll apply it on blots of the graph. Okay. So this is there's nothing special. These matrices also have a name. These are called, I think, primitive. I think they're called primitive matrices. They are not positive, but if you take higher enough, yeah.
So it's necessary that there exists a 2n plus 1 length path between any two vertices.
Yeah, just take the shortest path. That will be, if there's the shortest path, then you can maybe go on the edges, you can loop or something.
Yeah, but it has to be exactly on length 2n plus 1 for it to be positive.
Okay, so you are saying whether it will connect or not.
Yeah.
So if it's bipartite, for example, you're going to, there are problems. You could consider, wait, do I want to get into this? N is the vertex size, yeah, size of the graph, yeah. So let's see. You're saying if it's some periodic thing, then you'll have problems. I think I can just consider G to the 2n plus 1 or 2n plus 2, like I can add them up. I can consider sums of powers. So what I'm going to say is that any eigenvalue here is also an eigenvalue here. So if I want that, I can just sum over many powers of G and then that will be positive. That will still have the same eigenvalues. Yeah, I can do that, yeah. Yeah, they will get powered, yeah, but this largest one would stay the largest one. It will not destroy the order. But let's just write 2n plus 1, it's fine. But these matrices, they're called primitive. They are basically, you cannot apply Perron-Frobenius directly, you take powers and then you apply it. The Perron-Frobenius also applies to primitive matrices. Okay, so what does this tell me? This tells me that just by Perron-Frobenius, we get that the multiplicity, so this is my notation for multiplicity of, where is it? The multiplicity of lambda in G is at most the number of G, okay, because they are blot matrices, so the eigenvalue you can also just go blot by blot. In every blot I can apply Perron-Frobenius. The largest one can only appear once, so the multiplicity of lambda is at most the number of symmetry components in G. Okay. You should install those buttons. Like my hand is all automatically going there. That would truly mess with me. My hand is going there repeatedly. Okay, so this is this. Now let us get our bound. So I will just define k. This is a number that will be determined by lambda alone as the smallest graph. Smallest, well, if it's the smallest, it has to be connected. So let me just say smallest graph with lambda and infinity if no such graph exists. Okay, so this is a function only of lambda. I have a value lambda, it's a real number. Either there is a graph that has spectral radius, which is the largest eigenvalue lambda, exactly lambda, or not. If there is one, the smallest such graph has size k, that is my value k. If there is none, then k is infinity.
So this is some other graph.
completely.
Yeah, there's some draft. Like I'm doing all possible drafts. I'm checking what is their spectral radius. If it's lambda, then I say, yeah, this is my thing, Eureka, and then it's K. Okay. So if this is the definition of K, can you predict what I'm going to write next? So actually, let me write it, and then can you tell me why I wrote this? Wait, sorry. Okay, no, I missed a step. So don't tell me this. Don't tell me this. Tell me this. Yeah. So K is it's the smallest graph that has eigenvalue lambda. I can go over all graphs. I can go over them in a sequence. Either the largest eigenvalue is lambda or not. The first time I find a graph whose largest eigenvalue is lambda, I call that size K.
Smallest graph and smallest number of rows.
Yes. Yes. Smallest graph is so.
So I can produce like a certificate, which witnesses like allocated extra components. And that certificate is just paid issuance of this graph.
You're answering my question?
Yeah.
Okay, yeah. So yeah, that is correct. So the justification is that this lambda can only appear once for every connected component, and if it has to appear for some component, that component has to have size K. Okay, so if the lambda appears m times, then there needs to be at least m k vertices. In other words, the multiplicity of this is at most n over k. This you have to partition n into connected components. Each one should have lambda. You need k per component, so the number of components n over k. Okay, so k is a function of just lambda, and the bound I'm getting is n over k. Okay, so this is the thing I want to take away from this, and I want to finish the proof. So I have, just like here, I have that D is at least the rank of lambda I minus G plus J over 2. This is a rank 1 matrix. So I can write G minus 1. I will change this, so I'm just marking it. I will change this, I'll make it stronger. But currently, let's say it is minus 1. So the rank of this matrix, lambda is an eigenvalue. So the rank of this is just n minus the multiplicity of lambda in G, and again the minus 1. Okay, this I know is small, so it is greater than or equal to n minus n over k minus 1, and I can rearrange it. I will get some bound, so I will get n is less than or equal to k d plus 1 over k minus 1 like that. Okay, this is okay, but I want a better bound because I want it to be tight. So this is good enough. Like typically we don't care about constants, but I want it to be tight in a strong sense. So the claim I want to make is actually I can write plus 1. Okay, so let me argue why. Okay, so let us see. So let us examine this matrix and this matrix. Okay, so I have matrix 1, M1 is equal to lambda I minus G plus J over 2. I have M2 is equal to lambda I minus G. Okay, now this matrix is TST by assumption. This matrix is also PST because lambda is the largest eigenvalue. So any eigenvalue that is left, if you subtract it from lambda, you'll get something non-negative. Okay? So they are both PST matrices, and in fact, this matrix is also PST. It's just 1 transpose. Okay?
So lambda is stable because lambda is exactly the lambda singular. So lambda minus.
Yeah, but singular can still be PST.
Yeah, that's fine.
Yeah.
So therefore, you get that this one boost.
No, that's not how I get the +1 boost. So I'm just saying this is PhD by assumption, this is PhD by our choice of lambda, this is PhD by definition. Okay, so now let's see what happens if m1x is 0. So if m1x is equal to 0, then I get that x is in the kernel of, or let me say x m1 transpose x is equal to 0. So it's only in the kernel if and only if this is 0. This implies that x transpose m2 plus j over 2 x is 0. This is x transpose m2x plus x transpose j over 2x is 0. These are PST matrices. So the only way this can be 0 if both of them are 0. So I get x transpose m2 x is equal to 0 and x transpose j over 2x is equal to 0. Now why does that give me a +1? So lambda is the largest eigenvalue of G, which tells me that its eigenvector is entry-wise positive. Okay, so this thing m2x is 0 for an x that is entry-wise positive. Okay, but the x is here the eigenvector, that's why this is 0. So this m2x is 0 for an x that is entry-wise positive. For that x, this is non-zero because j is just 1. So if it's a sum of positive numbers, it will be positive. So there is something for which this is 0, but this is not 0. So I get that the kernel of M2 is a strict subset of, wait, something for which this is 0. So I want, yeah, kernel of M1 is a strict subset of the kernel of M2. This is again by Perron Frobenius because the largest eigenvector is positive. There is one thing in the eigenspace that is positive, for which this will not be 0. So I get something extra in the kernel, which means the rank of M1 will be 1 smaller. So the rank of M1 is 1 larger. I don't know if I'm either smaller or larger, but I think it's correct. Okay, so this is why you get the +1. Let me write the +1. This would be +1. This would be +1, and this would be -1. Okay, and this is the bound that I want to keep. So I want to say that in this case here, let me just write n is less than or equal to d plus 1. Here G, and here n is less than or equal to k minus 1, where k is defined as, here it's the smallest graph that has that spectral radius. My construction will give me exactly this. So it's not exactly this. For example, this may not be an integer, so there will be a floor or something, but it will give me that with a -1. Okay, but these are the two cases. Okay, case case 3 is what is left. So lambda is an eigenvalue. But not the largest. Okay, so this is the only case that is left, and let me also draw that thing from before. So G to the sum power is equal to okay. So now we're in this case where I know lambda is an eigenvalue and it's not the largest one. Okay. In this case, again the proof will go in a very similar fashion. Again, what I want to get, want an upper bound on the multiplicity of lambda in G. If I have that, the rest of the argument we didn't use the case at all. It was just the multiplicity bound that used that. So I want to get this bound, and to get this bound, let us first specify what lambda should be. So lambda cannot be any eigenvalue of G. We know it's not the largest, but we can in fact say that claim 1 is lambda is the second largest. And this will use the PST-ness of this matrix. This will be the first thing I will say. And the second thing I will say is that lambda, so by the way, this even with multiplicity, like there's only a unique largest one with multiplicities. The second is with multiplicities. And the second thing I want to say is lambda is in, or let me say, lives in the same component as lambda 1. Okay, so I'm saying two things here. The first thing I'm saying is fine, lambda may not be the largest eigenvalue, but if it's not, it must be the second largest eigenvalue. When I say with multiplicity, I moreover mean that the largest one has multiplicity 1 and the second largest one is lambda 2. What claim 2 is saying is, again, you have this blot matrix. The largest one would be in some blot, it would be an eigenvalue of some component. The second largest one is also in the same component. Lambda is also in the same component. With all the multiplicities. All of them are living there. Okay. You cannot have it outside. The outside ones are all smaller. Okay. So this is the interpretation of these claims. Yeah. So any eigenvalue here, the eigenvector would correspond to one blot. So it is blot matrix, right? So that is what lives in it. It's also an eigenvalue of that component. Yeah, so we have to prove these two things. It's the second largest and that it lives in the same component. Let us prove them one by one. So this is proof 1. Both of them will be by contradiction. Okay, so they're not very hard, but they're a bit of linear algebra is needed, so I'll go over them slowly. So suppose not. Suppose not. What does that mean? Then there are at least two numbers, two eigenvalues that are larger than lambda. Okay. Then there exists, there are, let's call them lambda 1. It may be the same as lambda 2, but they are both larger than lambda. That are eigenvalues. Okay. So um, consider the span of lambda 1 and lambda 2. Yeah.
When you are done, what you essentially showing is that, what you also show is that lambda 1 has multiplicity 1.
Lambda 1, yeah, just by this, just by this. Yeah, that will come in claim 2. Actually, it will come right now. It will come in right now. So consider this. I'm counting them with multiplicity. So this span has dimension 2. Okay. Moreover, I know that the null space of J n minus 1. Okay, it's 1 1 transpose. There's one eigenvalue, everything else is null space. Now the ambient dimension is n. This is dimension n minus 1. This is dimension 2. There must be an intersection. So there exists a vector v. It's not zero. It's a non-zero vector v in the null space of J. In the null space of J and in this span. Lambda 2. Okay. So let us see what it would be. So V transpose that whole thing to V. Now it's in the null space of J. I can get rid of this. V. Okay. This part will just give me lambda times the norm of V. Okay. What would this give me? Well, it's in the span of lambda 1 and lambda 2. So this thing, whatever it is, it has magnitude larger than lambda. Strictly larger, because they are both strictly larger. So whatever this number is, it has magnitude larger than lambda. So this thing is less than this, which is equal to 0, which contradicts the fact that this is PSD. Okay, so this is the contradiction. Okay. So this is the proof of claim 1. This is unique, and even the multiplicities, this is second largest, and even multiplicities it is the second largest. Okay, so let us get to proof 2. I think that's all I'll have time for. Wait, when did I start? 3:30. Oh, then I have lots of time. You are going to suffer now. Okay. So this was proof of the claim 1. Now let's prove claim 2. Again, it will be linear algebraic proof. Same contradiction argument. So suppose not. So what does this mean? Suppose that the largest eigenvalue of lambda 1 lives in C1 and the eigenvalue for lambda it lives in C2. Okay. So let's call it V1 be the eigenvector for lambda 1. Okay, this has support on the vertices in C1. Let's just call it V be the eigenvector for lambda. This has support on the vertices in C2 or in a different component.
It's an eigenvector for lambda because
Yeah, sure.
It's some eigenvector which lives in different components.
Yeah. Yeah. So this is supported on C1, this is supported on a different component. They're supported on different components. That's the point. The fact that they're supported on different components means that as they are supported on different components, lambda is the largest throughout. I already showed as the second largest, so there is the largest throughout. That's wait. Oh, lambda. Oh, yeah. Lambda is largest for that number. Yeah, you're right. Yeah. Yeah, I thought you were talking about it. Yeah. As they're supported in different components, they are non-zero vectors. So there exists a value C such that this is a real number. C is a real number such that V1 minus CV, this guy, all its coordinates sum to 0. Okay, so this thing is non-zero, it has a certain sum. This thing is non-zero, it has a certain sum. So they live with different components, which means they are the largest eigenvalue for their components, which means their eigenvectors are positive. So this thing has some positive sum, this is some positive sum. I just take C to be the ratio. It's again, whenever you have the largest eigenvalue, you can apply Perron probabilities. They have a very nice structure on positive matrices. So there exists something such that this thing sums to 0. Equivalently, 1 transpose this is equal to 0. Okay. So this is what I have. Now let us apply the only technique we have is PSTness. We have V1 minus CV transpose all of that. Okay, this has to be there. I want this sum to be 0, which means this J term will just vanish. So this is non-negative. Now you can expand it out. You'll have terms that have V1 matched with V1. You'll have 2 of them. You'll have terms that have V matched with V. You have 2 of them, and then you have 4 cross terms. So you have V1I V and VI V1, and then you have V1I. What are the other? V1G V and those 4. I claim the cross terms all vanish, and the reason is that the supports are disjoint. Okay, so V1 is supported on some subset of coordinates. V is supported on a different subset of coordinates. V1 inner product with V would vanish, and the same even after I apply the graph, because the graph would keep the component preserved. So even V1G V would vanish. So all the 4 cross terms will vanish. I'll be left with only the regular terms, which are lambda times V1 transpose V1. That is the first one. What are the other ones? Lambda, I think G1 would be the other one, minus V1 transpose G V1. This would be one term. Yes, C squared lambda V transpose V, and minus C squared V transpose G V. Okay, so this is what I'll have. Now let us just use the fact that these are eigenvalues. So GV is just lambda V. So these 2 will cancel. Okay, and GV1 is lambda 1 V. So I get that lambda V1 transpose V1 is greater than or equal to lambda 1 V1 transpose V1. This is a norm squared. This is a positive number. I can get rid of this, but this is a contradiction because lambda 1 was the largest one. So this is greater than lambda, which is around h. Okay. So I have proved these two things. This is a very strong structural statement. I'm saying that if this lambda thing was not the largest one, then this TSDness of this matrix implies that it has to be the second largest one, and moreover it has to be in the same component. So there is one component that has both the largest and everything that is the second largest. All the other components that are lambda 3 and below. Okay. There are two eigenspaces for, yeah. Basically, you always want to remove j. This is a very natural thing. This is the action of an eigenvalue. You always want to remove j, and if they are distinct, then there is a clean way to remove j like this, which will remove all the cross terms.
But like I meant without like doing the maths or something, is there like something that I can say like one sentence? I can see that it should be obvious to. The question is why was this substance apparent to the authors? Because in this proof, the most important point was that G1 lives inside that component only.
Yeah.
Like which enabled us to cancel the cross terms.
Yeah.
So some like that is a bit mathematical in my opinion. No, I was just asking if it's very apparently obvious that why this should happen. Like, is there?
I'm not sure if there is a simpler statement I can give. I would think that it's a natural thing to try and combine them, but I don't know. I don't have a good answer for that. Yeah, I don't have a good answer for that. Okay. So we now have a couple of structural properties. We know that the largest lambda is the second largest one. We know it lives in the same component. Everything else has a smaller one. So basically, we are only worried about the multiplicity of lambda, which means we can restrict attention to one component. Nothing else has lambda. Only C1, let's say C1, that's the only thing that has lambda, which means we can assume that the graph G is connected. So let us note that. Okay, I don't think I'll have time to prove this, so I'm going to state it, and then we will see later on how much I can prove this. So the lemma I want to say is in any bounded degree, there's some degree bound, let's say delta, so let's say it's delta bounded. Connected graph G, the second largest eigenvalue has multiplicity at most n over log n. Okay, so what I have shown so far is because of these two claims, I can focus my attention on C1, which allows me to conclude that G is connected. There is a different argument entirely. I will not do that. It is sort of a Ramsey theory type argument, like the constants are used there. But using that, you can always also assume that the graph is bounded degree. I will not say more about that, but this is not the main part of the proof. The You can assume that just like I proved connectedness, you can prove the bounded degreeness of it. And then what I have is a graph G that is both connected and bounded degree. And this is giving me exactly the bound I want. I have the multiplicity bound on lambda. It says that the second largest eigenvalue is multiplicity at most n over log n. Okay. This is the lemma I will use. Let me say a few words about this first. So one thing is that you need the graph to be connected. So let me say remark 1. Remark 1, G must be connected. G must be connected because a perfect matching or even just the empty graph iris would be counter example, but let's say a perfect matching is a counter example. So a perfect matching is just n over 2 edges that connect two different vertices, and the matrix would look like 0, 1, 1, 0, 0, 1, 1, 0, so on. So whatever eigenvalues you have, you will have multiplicity n over 2. Okay, it will not be n over log n. Okay, so you need connectivity. You also need bounded degree. The degree bound is small. Bounded degree. You also need bounded degree because K n n is a counter example. So K n n, the matrix, it looks like you have 2n by 2n. This is all 0. This is all 1. This is all 1. This is all 0. It has one positive eigenvalue. I think it will be root n or something. N or root n? Yeah, n. Yeah. Yeah. There will have one positive eigenvalue n. It will have minus n, and then everything else will be 0. So the multiplicity of this would be n minus 2, which is again too large. Okay, so you need both bounded degree and connectivity. But if you have both, then you can prove this. You can not only prove this for the second largest eigenvalue, you can prove this for the jth largest eigenvalue also. The only thing that changes is this constant here. So this thing depends on j and delta, and the j would just go here. So you can prove the same bound. Okay, so you're getting a sublinear. So the multiplicity can be at most n. I'm saying it's sublinear. It's n over log n. It's not very sublinear. It's only a log n away. You can ask, a natural question would be, what is the best lemma of this sort? Can I improve this number? Maybe you can, maybe you can't. But there are graphs where this is omega n to the 1/3. So you can't improve it below this number for general graphs. So yeah, this is, I think this is open. I didn't find anything. Yeah. Yeah, I don't know what the right answer is for this quantity. There is insertion for cube root n, there is n over log n, those are two bounds, that's all I have. But what I'll be using is this sublinear thing. Okay. No, the delta goes here. The delta goes here. Yeah. It goes in a constant. Okay. So we have this lemma. Let us finish the proof assuming this lemma. So we have that the rank of this matrix is at most over 2. This is a rank 1 matrix. This time I'm anyway going to lose this, so I might as well lose a 1. So I'm losing the 1. This is the second largest eigenvalue. It is a connected graph because it's in the same component. I can delete all of the components. I have not shown boundary degree, but there is an argument that can show it. So I can apply this lemma. So this is and minus 1 is also here, which tells me that n is less than equal to d plus, I think, or log t. So they are linearly related, so logs are all the same. Okay, so this is case 3. Case 3. Just, and here I get n is less than equal to d plus. Let me just write little o of d. Okay, so let us combine them and let us write our theorem. So the theorem, it would say we had a question. Where is the question? This is the question, and the answer is let k be the size of the smallest graph with spectral radius lambda, and k equal to infinity otherwise. I won't write it. It's k equal to infinity otherwise. We have n. Okay, so I think I told it n alpha d. N alpha d is less than equal to. So if such a graph exists, if there is a graph that has that spectral radius, okay, then this is the largest number. So for large enough d, this is d plus o of d, this is d plus 1, this is d times something more than 1. So for large enough d, that is the best one. This is k d minus 1 by k minus 1, and this is for large enough d. Okay, this should be larger if d is small, so I'm just saying large enough d. If k is infinity, if there is no graph with eigenvalue spectral radius lambda, then this case is not possible. So I just get it is d plus little o of t. Okay. So this is an upper bound on the number of. You have something to say?
K shows up, like I mean, this K lambda shows up when, it is, so when K lambda shows up, correspondingly it's case 2, which, the bound of case 2 is what you are using.
Yes.
I think that K lambda is less than everything, case 3 is also could be a valid choice.
No, this is for if d is large enough, then this is the largest one. Whereas d times something more than 1. This is d times something 1. This is d times 1. This is the largest one. If I say this, then I'm covering everything. So for large enough d, this is the number. In fact, you also can have a floor here because and if no such graph exists, then this case is not possible. So this is the best bound, right? So this is d plus or d. Yeah, because there's no graph with that spectral radius. So that is the bound. This is the theorem. It is also tight. So let me quickly say that. lambdas that can't appear as that.
Can I comment that maybe lambda is some weird irrational number?
I mean, so these are the roots of the characteristic polynomial, so it will be algebraic.
Yeah, definitely.
It will be algebraic. Within algebraic, I'm not sure. Mrinal, do you know? What are the eigenvalues? So this is some graph with zeros on the identity, some 0, 1 graph. You want the largest eigenvalue. I don't know much about that. It should be algebraic for sure because it's the root of the characteristic polynomial. Yeah, so this is the theorem. Tightness. So let us see. So this one, I already kind of showed that it is tight. So even if you don't care about the signs, even if you have vectors and not lines, I gave you D. So this one is tight up to the O of D term. This one is also tight. So suppose K less than infinity and consider a graph. So let this graph be J and let let H be the graph, the smallest graph or the graph exhibiting K. Okay, so this is a graph with spectral radius lambda. I just define G to be D minus 1 over K minus 1 disjoint copies of H, and then I know that this I know that the number of vertices here would be, for every copy I will be able to remove one multiplicity, so all my calculations would be tight and therefore I will get, so the number of vertices is exactly this. Actually there's something interesting here, so if I have a couple of, let me tell you why there is a minus 1. I think that is a bit interesting to note, so let me write it here. Okay, so this minus 1 actually, this is what makes it tight. So consider this graph H, this is the smallest graph with spectral radius lambda, and I consider this many copies of H. Then let us see what is lambda I minus G. Okay, so lambda is the largest eigenvalue by construction. So this is a PSD matrix. It is a PSD matrix. It has rank G is equal to n minus the multiplicity, which is D minus 1 over K minus 1. So n is K D minus 1 over K minus 1 minus minus D minus 1 over K minus 1, which is equal to D minus 1. So this rank is D minus 1. But if I add J over 2, I get D. So this minus 1 actually, otherwise I would have gotten something D plus 1 this. But yeah, this is the theorem. This was the main lemma that I did not cover. I also did not cover the boundary degree part. But essentially the proof is you first reduce it to a graph problem, then you reduce it to a multiplicity problem. You have to bound the multiplicity. In these two cases, the multiplicity bound is straightforward. Here you need to do this trick. You need to invoke this lemma. This is the key technical lemma. This is the bound you get, and it is tight up to this term. And even the floor sign, you can write the floor, that is the right number. So yeah, any questions?